Okay, so up next we have Marcio Taddei from ICFO. The floor is yours.
Hi there. Well, good morning. Thanks to the organizers for having me and allowing me to talk a little bit about my work. This is a work that we have done about in collaboration with all these people here from different institutions, and it's, I guess, slightly more practical than some of the works that have been presented here. But I guess it was interesting to bring it here to show how some of these things related to quantum computing, how to make them fit into, say, a problem that is a bit more practical, right? So we know, I guess I don't have to talk too much about NISQ devices. We have had great talks about it, right? But I guess the important thing is, well, we have very few qubits available, right? So whenever we're on the, say, algorithmic side, it's like we have this little zombie here that says, well, use less qubits all the time. We don't have many qubits, right? So this zombie is going to haunt us, and we're going to try to run away from it. That's kind of the summary of my talk. But still, stay with me. Don't go away. Well, of course, we can try to look for different kinds of quantum hardware. For instance, quantum annealers that can have up to, say, 5,000 physical qubits. But of course, then it's an annealer. It's not circuit-based. But we always have this kind of problem, right? But then we are going to take a very practical problem and apply onto quantum annealers that are dedicated to QUBO, which is, well, quadratic unconstrained binary optimization. And let's see how this works, right? So in a real world problem, right? So what's the problem, right? Let me explain it a little bit, because I guess the point is to make something practical or practical inspired. The problem is related to satellite image acquisition. Basically, we have a satellite that goes, well, around the Earth. It hovers around a certain path, and it can take photos along the path of different things, and along that path there are many requests for photos to be taken, right? And in fact, there are too many requests, and we have the problem of saying, okay, which of these requests should we do? Which photos should we take? Which photos should we just not take because we cannot take them all, right? And it's interesting that there is a very nice data set. It's this reference here. It's called Spot 5, which is basically a data set of photo requests made to the satellite. You see how this problem has shown up in different, with a certain frequency. And basically the thing was, this data set has some characteristics, which I'm not going to go into too much detail because I'm going to run out of time if I do. But basically, I guess the main thing is, well, we have the request, we have a certain weight, which is how much, say, you get paid, if you want to think like that, how much you gain by taking that photo, which is what you want to optimize in the end. And we have some variations of how to take these photos, and well, this is important for later, so I'll mention it here. So some photos can be taken with either of 3 different cameras, and some photos require 2 cameras at once, right? So there are these 2 kinds of different requests that are made, right? And on top of that, we have some constraints, right, which is very necessary. We cannot take all the photos because, I don't know, maybe these 2 photo requests here are just too close. The satellite cannot just aim for one and then for the other, for instance, right? There are other sources of constraints, but I guess that's a main one that I'll mention here, right? And then we have these files here that describe these things, these constraints. And it's nice that this data set goes from something very small, which is actually this example, something much bigger, so we can try it on, I say, an increasing size of the problem to see how it works and how a quantum computer can work with these things in different size problems, right? Right. So what's the hardware we're going to use? We're going to use quantum annealers, which I guess haven't been mentioned that much here. So I'll briefly say, well, the point of quantum annealers is, well, it finds the ground state of this guy here. It's a very short description of quantum annealers. That's what we need right now. We have the topology, which defines basically, well, these are Pauli Z, right, gates. We have all the Zs here, and these 2-qubit gates, well, we have some of these pairs, which are, say, the pairs that are connected here, they're linked here, right? The pairs that are not linked, we don't have that available, so the hardware cannot choose any J here. It's as if J equals 0 for them, right? And of course, if you go to different generations of D-Wave, this is just D-Wave, it could be anyone, any quantum hardware, it gets more and more complicated. These are the 3 different, say, generations of it, and we get more connectivity, so we can apply it to more problems. And well, how does it connect to QUBO? Well, basically the thing is, this is very much well, writing this ground state here is very much finding the minimum of this expression here, where x is a string of bits, say with values 0 and 1. Well, here we have spins which can be plus or minus 1, but it's a simple conversion from one to the other. And q is, well, some matrix, right? So we have this quadratic expression in x, which is quadratic because, well, these guys here are quadratic. We don't have a Hamiltonian with the third term z1, z2, z3. We don't have that available in the hardware, right? So we can only do these quadratic things. But of course, the problem itself we have is not cubo, it's not quadratic, right? If we write the, first of all, we have constraints, and the U stands for unconstrained, so we have to adapt that, and which we do including penalty terms. So we include penalties to the function that we have to maximize. I'll give you examples in a bit. Well, actually, we have an example here, but I'll talk about it later because of my time. And then we have to discuss how to encode the variables we have, right? We have these variables, we want to encode them to use them in this quantum computer. Well, there is one way which is a little bit naive, but bear with me, of saying, well, I have a request, some request I, and I give you 4 variables, right? 1, 2, 3, and 4. Meaning, take the photo with camera 1 or 2 or 3, or take the photo with the 2 cameras at once for that stereo, more complicated photo, right? And then, given that, then basically we have to minimize this function here. These are the weights, which is what you gain by taking the photo. This is basically 0 or 1. And we have some constraints, right? We have the constraints of not taking the same photo twice, because that's not going to give you anything. We have some constraints intrinsic to the problem that deal with 2 photos at once, or even 3 photos at once. And we have some constraints that, well, if your photo is of the mono kind, that takes only one camera, you shouldn't use that 2 cameras on it, and vice versa, right? Just to respect the kind of photo you have. So we have this bunch of constraints, and you have to use penalties to write that, to use that, right? So I guess one simple way of writing a constraint is like this. Well, say you have these 2 variables, they cannot be 1 at the same time. What do you mean by to write a penalty? Basically, I minimize a function to which I add this term here, right? So if both are 1 at the same time, I'm adding this term such that my minimum is driven away from anything that has 1, 1 here, right? That's the point of adding this penalty. Of course, if it's more complicated, say I have something like this, right? I have these 3 variables, and 2 of them can be 1, but not all 3, right? How to write that? Well, there are ways of doing it. Some ways are intrinsically quadratic. You have your variables and some extra variables here. It's all quadratic, so it fits into the quadratic part of the problem. It has its disadvantages because we need 2 extra variables here, 2 slack variables as we call them. We have a more cubic way, so if we write it like this, well, if all of them are 1, which is violating what you want, then you do have then you're adding something, so your minimum is driven away from anything that has 1, 1, 1 here, which is what you want. But then this is cubic, right? If this is cubic, you can't really do that on Cubo, right? Cubo is quadratic optimization, right? But then, because we can only do Cubo, well, what we can do, I guess what we need to do here is what we call reduction to quadratic. So what's reduction to quadratic? If it sounds long, I'm going to get to a nice conclusion in a short while, right? Well, reduction to quadratic means, well, I have some polynomial, and I'm going to find an equivalent polynomial that only has quadratic variables. By equivalent, I mean, if I want to minimize this thing here, well, the solution of these 3 variables is the same as the solution of this minimization here. This minimization has, say, the price of an extra variable, s, some slack variable, name given to it. But it's all quadratic. You have x1, sx2, everything here is quadratic. So it can be done on a quadratic, say, machine. So it can be done on a quantum annealer, as of the ones we know today, right? And of course, there are other ways of doing it. I don't have time too much to go into that, but there are different forms of doing these reductions to quadratic depending on the term. This is, I guess, a simple example so that I can convey the idea to you. There are more complicated ways of doing it, and we even thought of a way which is sort of mixed. And why am I telling you all of these, which sounds like maybe giving you sort of lots of details? To try to compare some different encodings given these penalty terms, given these reduction to quadratic, right? So I guess it's not too hard to see that that encoding I showed before is kind of wasteful, and we should reduce the number of qubits. I guess it dedicates a variable to something that you know you're never going to use, right? If your photo can only be taken with two cameras at once, it actually dedicates variables to be able to take that photo with one single camera. It's wasteful. It's clearly wasteful, and I guess the first thing we can do is, well, instead of defining four variables for everyone, well, define just three variables if the photo can be taken with one of three cameras, or just define a single variable if there's only one way to take that photo, right? And well, of course, this is helpful. This reduces the amount of constraints you have, so it reduces the amount of penalty terms. And well, you can actually see it here. The size of the problem decreases a lot when you do that. This graphic way of showing, and which is good. But then we can think of even denser coding, right? And this is the non-intuitive part here. Let's say for the photos that we have that we can take with three different cameras, let's think of this encoding here. What is this encoding showing? Well, I'm using the minimal amount of qubits, which is just 2, to encode these 3 possible outcomes, right? You can not take the photo because it's not the case. It's better to take some other photos. You can take it with camera 1, 2, or 3, right? Like this. This is a denser way of encoding that, right? Which in principle is good, right? We want to use less qubits, so using less qubits for that should be good. And the problem is, and that's why I mentioned so much those penalty terms, is that while you cross out some extra constraints here, which is in principle what the zombie ever wanted, there's a problem there. When you have some of the constraints, let's say we have something like this. We have a constraint that involves 2 variables, right? In the encoding I showed before, this basically appears as this quadratic term, right? So this constraint involves 2 photos, and we have these kinds of terms here, which are quadratic, which are all right. Like for the same thing, but using this denser encoding, well, we can draw this Carnot map, which is something people study in electronic engineering, and basically we can see that we actually get these kinds of quartic terms here. Because you're using a denser way of encoding, you actually end up with these more complicated terms here. And then what happens is, well, because we have this higher order term, we actually have to reduce it to quadratic. And then to reduce it to quadratic, we need more variables to do that, right? In the end, well, I guess the same thing for cubic, but I shouldn't waste too much time on it. I guess I want to show these graphs here, right? The thing is, with that dense encoding, in principle, you have less variables used, so the standard being the red and the denser one in the blue. So you see the blue ones are always underneath the red, meaning you use less variables originally. But then when you take into account all that reduction to quadratic, what you get is this thing here, where the blue with the denser encoding actually ends up using more variables than the original one, because you need to do that reduction, because quantum computers, quantum annealers, nowadays can only do quadratic terms. So something that would be a gain to reduce the number of variables originally, actually, because of our hardware limitations, current hardware limitations, ends up being something more complicated, ends up giving us more variables than before. So I guess that's what I wanted to say. I guess the zombie is unhappy with that. And yes, that's the basic conclusion I wanted to say. Of course, encoding is drastically relevant because we don't have many qubits available, but it can have counterintuitive results, right? It's not simply the denser the better, right? And thank you for your attention.